Hi everyone. Today we're going to go over the electron configuration of copper. Now, if you're in one of my chemistry classes, I have briefly mentioned that copper has some exceptions as far as what the electron configuration is. And we haven't in class done the electron configuration for copper, but today I'm going to do it for you. I'm going to show if we follow all of our rules, what the electron configuration of copper would be if we followed our rules, and then why it's an exception to our rules and how we correctly write it. So copper is an exception to our electron configuration rules. It is, and let me circle it on our periodic table, it's right here. Copper, when it's neutral, when we're talking about a neutral atom, it has 29 electrons. Now, I have all of our information here. We have how many electrons can fit in each orbital. An s orbital can hold up to 2 electrons, a p orbital can hold up to 6 electrons, a d orbital can hold up to 10 electrons, and an f orbital can hold up to 14 electrons. I also have the filling pattern here. We go from 1s to 2s, then to 2p, then 3s, and so forth. So what I'm going to do first, and I'm going to put this in blue font. Actually, I'll do red. I'm going to do in red font, if we followed the rules, what the electron configuration of copper would be, and then I'm going to talk about why it's incorrect. Now, this is for copper, which is an exception. For all of the other ones that we do in my class and you might be doing in your class, they're going to follow the general rules. So I'm just going to talk about one of the exceptions to the rules. In the case of copper, we have 29 electrons, so we're going to start here. We're going to go 1s2, 2s2, so we're following this. Then we're going to keep going and we hit 2p6. So we filled 10 so far. 2 plus 2 is 4, plus 6 is 10. We have 19 more to go. We hit our 3s. I'm going to put 2 in there. That's 12. We come around to 3p. I'm going to put, oops, I don't know what happened with my pen. We're going to put a p there, and I'm going to put 6 in there. So in this case, I have 1s2, 2s2, 2p6, that's 10. 3s2, that's 12. 3p6, that's 18. So we're still under our 29. We're going to keep going. We have 4s2. And then we're going to come around here and we have 3d. And let's count up. We have 1s2, 2s2, 2p6 is 10, then 12, then 18, 19, 20. That means we put a 9 here. Now, in this case, we have, if we followed our rules, our electron configuration. Now, for orbitals, orbitals are more stable if they're fully filled or half filled. So what happens is these electrons right here, it is much more stable for the 3d to be filled, which also makes the 4s half filled, than for this fully filled and 9/10 filled. It is more stable for this one to be fully filled and this one to be half filled. So orbitals are more stable if they're fully filled. They're also more stable if they're half filled. So the way that copper actually exists is 1s2, 2s2, 2p6, 3s2, 3p6, and then 4s1, which is a half-filled orbital, and 3d10, which is a fully filled orbital. So when you're doing these, copper does have this sort of exception where that electron jumps to the 3d orbital and we have the half-filled 4s and the fully filled 3d. It is much more stable in this purple one, and this is our correct electron configuration. Now, in one of my other videos, I will talk about, for example, chromium, and chromium has that similar exception like copper, we're going to sort of move around electrons from that 4s and the 3d because, again, fully filled and half-filled orbitals are more stable than other types of partially filled orbitals. So chromium has a similar situation, which I'll talk about in a different video.